recording. Yeah. Maybe you can click the OK, then it will not block the time. Okay, so good afternoon, everyone. So it's our NLP again this week, and we have our Kevin, his CBB, CBB program PhD student here to give his talk on his recent work, on the interpretability of large language model. Yeah, maybe you can introduce yourself and start the talk.
Hi guys, my name is Kevin. I'm a second-year PhD student in the Computational Biology and Bioinformatics program here at Yale. I work under Dr. Hua Xu in the Clinical NLP Lab. We are part of the Department of Biomedical Informatics and Data Science in School of Medicine. Now, let me start right away by saying that this is not my area of expertise. My work actually concentrates on characterizing mental health conditions using NLP methods and wearable biosensors. And as such, I don't work directly with large language models. However, I will say that I believe that this is a crucially important subject, especially in clinical applications, as large language models have kind of stolen the spotlight from other methods in AI and have kind of vaulted AI into the public consciousness over the past couple of years. And I think this is a good opportunity to present some literature that I found really interesting that attempts to advance our understanding of large language models and their mechanistic underpinnings. Again, I hope to try and inspire some more interest in this within our interest group and at Yale, even through kind of my amateurish interpretation of the subject. So you're no doubt aware that large language models have kind of stolen the spotlight in natural language processing and have been what some people call a revolutionary advance of the field. As interest has grown in their usage, one thing that has come up over and over again that has been a persistent topic of conversation between users of the models, providers of the models, and deployers of the models has been how black boxy they are. People don't really understand why they work and why they produce certain responses. And this kind of lack of understanding even extends to people who supposedly wrote the models. And this has kind of been a topic of interest in literature and mass media. And this is a selection of news articles and different literature articles that I just pulled. So you can see there's a massive amount of interest in this subject, even though the research is quite nascent. But in case you are kind of unaccustomed with what a black box is, let me explain. The idea is that, as I kind of just alluded to, modern AI has really started to permeate all sectors of society, and including sectors that are considered high risk, where AI making decisions might actually impact people's lives directly. And these sectors would include things like healthcare, law enforcement, criminal justice. Especially, we are concerned with clinical healthcare, but kind of the widespread availability and the ease of use of these systems has massively increased AI's popularity. And as AI's popularity has increased, it's kind of interesting. The models are also growing bigger, and as they grow bigger, they also grow more and more opaque and unknowable. And we call these systems black boxes. And what that means is an input goes into the model. We don't know what happens, and then we get an output. So we don't really we have like a lot of trouble explaining what might be going on inside the model. And I lifted this wonderful figure from a meeting. But yeah, so what, right? You could argue that in modern society, we don't need to explain why certain things work. You drive a car almost every day. you understand how like the internal combustion engine really works. That's a bad comparison because AI is different. In AI, we use systems to make decisions for us or support our decisions. And that can involve decisions made by public authorities like governments. On a moral and ethical stance, a very strong argument can be made to know what exactly the logic is underlying these decisions. And I would say, I personally would argue that it is unacceptable that an AI system that is making decisions for the general public has literally unexplainable and unknowable logic behind its decisions. And let me make this more concrete. Why do you want explainable AI? The first is something that I just covered. Specifically with regards to large language models, they are currently mostly black boxes and can generate really high quality responses that sound a lot like human beings. But sometimes we don't really know, most of the time we don't really know why they make certain decisions, why they are hallucinating, why they say certain things, why they might respond in one way to a same prompt, in a different way to the same prompt. The second is more nuanced. Our current understanding of large language models is based entirely on their training data. And as such, if the training data is biased, then the model itself will absorb and then spit out the same bias in their training data. The third one is kind of a consequence of the first two. You can tell that a lot, as AI has kind of grown more prominent in the public consciousness, naturally, there will be people who suspect or are less trusting of AI. And if we want more adoption of AI, and if we want safer AI, then we need to respond to those suspicions by building trust, which is critically important in high-risk fields like healthcare. And on a more practical level, there are increasing numbers of regulatory bodies and governments that are introducing laws and regulations that govern AI. And if we can't motivate ourselves to care about interpretability, they will force us to do so. So for instance, there's this Artificial Intelligence Act of 2024 that will take effect this year in the European Union. I'll just briefly have a sidebar on this later. But there are specific provisions in the Artificial Intelligence Act that mandate interpretability and explainability for certain AIs. And they have a whole section on artificial general intelligence that requires that there's some kind of documentation on it that explains how it makes its decisions. And on a technical aspect and a more practical level, explainable AI is easier to debug and train and improve. And as such, you can see why explainable AI is easily motivated. Now, let me place this in context. Actually, the explainability movement is not new. It has kind of a long in an AI sense history, with initial efforts in deep learning. Here I pulled some what I consider to be pivotal publications that cover earlier efforts in deep neural networks to understand mechanistically what they are doing. Of course, I have to include the crucial publication in 2017 that actually introduced transformers, because what's interesting is that in this publication, the attention mechanism is actually one of the first built-in interpretability tools that allowed researchers to see actually which parts of the model input that the model was currently focusing on. And as you kind of move on into the 2020s, this is when transformer models began to gain prominence. And I really like this publication from 2020 from the University of Washington. The authors argued that essentially large language models are only probabilistically predicting the next word without understanding semantically what they're generating, which means that they kind of live and die by their training data, and they don't know if what they're saying is incorrect or appropriate. And if the data set quality is not good or is actively malicious, then they can be, quote, dangerously wrong. I still like this, this interpretation or this kind of warning, even as large language models have had improved safety mechanisms that can avoid something like this, even with bad data. I think it's a good standard to live by. AI systems are only as smart as we can make them as of right now, and they are only as safe as we can make them. So in the present, there's kind of been a growing focus on law and ethics. And I think these three papers are, well, the third one is kind of the whole, it's a paper in a sense that it's a body of papers. But I think the first two are really good because they come directly from people who work directly in this field. I think for instance, the first one comes directly from AI. And it kind of frames the need for interpretability in kind of an existential sense. Like artificial general intelligence has the potential, maybe in the far future, but the potential to surpass humanity and overcome human interests irreversibly so. And as such, I think right now, the authors argue that there needs to be ongoing and substantial efforts to try and make sure that artificial general intelligence is aligned with human interests, and more interpretable AI, more interpretable AGI is one of the crucial stepping stones to ensuring that every aspect of the model is understood by humans and definitely advancing human interests only. And the 2023 paper that I found it kind of takes that to an extreme. And I think this is necessary to imagine. It's, what happens if AI is actually actively harmful and misaligned? It kind of observes that there is this trend right now of higher intelligence, higher prediction, higher predictive power, more powerful models that subsequently have decreased interpretability. And the authors argue that this is the wrong direction, or this is a dangerous direction to be going into, and one should always keep in mind the importance of transparency and interpretability. And I think something really good to focus on right now, the actual implementation of some kind of regulation that controls AI and its development, is this Artificial Intelligence Act written up by the European Union. And it covers basically all AI, except certain exceptions for military and national security and research applications. And I really want to focus on how this is kind of coming for all of us. Like it's this law defines kind of 5 levels of risk of harm for AI applications. And I think what's really relevant to our lab and a lot of our interests is this high risk category. And I think people who are developing AI that has applications in health, much like our lab, we have a moral obligation and now a legal obligation. This is only for the EU right now, but I can't imagine that it will take that long for it to become a thing in the US, to make sure that our AI is transparent and has absolutely an understandable to laymen mechanism. We need to be able to explain why our AI is making certain decisions. And I think for general purpose AI, they have a completely separate category. Whereas for models like ChatGPT, OpenAI would be the target of this kind of legislation. And I think for just imagining that we are, like, our lab kind of develops a system that will classify certain, for example, certain texts as coming from a depressed person and certain texts coming from a person who's not depressed. We need to be able to explain how the model is classifying which text is depressed and which text is not depressed. And that's just the basic idea of this, because we, sooner or later, this is going to be something that catches up with us, even if we don't think about it too hard right now. Because I think in academia and in industry, there's a very high focus on producing results and also producing something that can be marketed. And I think this is something that is important not to lose sight of. And back to the timeline, I think right now, I think there's finally some, as LLMs have kind of matured and taken the spotlight, there have been efforts, kind of successful efforts actually, and I'm going to talk about 3 papers today that have results, seemingly promising results that outline promising directions that we can go in for how to interpret how LLMs work. And I'm going to talk about 1 paper from Anthropic, 1 paper from OpenAI, and 1 paper from this group at Oxford. They cover very different aspects of interpretability, but I think they are all interrelated and they are all worth talking about. The first paper comes out of OpenAI. Now, this is actually slightly outdated, but it was released last year, and this publication goes over an attempt to explain what individual neurons are doing in large language models. And somewhat ironically, they use a large language model to explain what a neuron in another large language model is doing. You can probably imagine that the results aren't very good, but I think this is a very good proof of concept paper to look at, because it's one of the first papers that actually it shows like an initiative on the side of the provider of the AI to try and make sure that their AI is interpretable. Now, so what they did was, okay, so let me back up first. The researchers motivate their research this way. To understand the large language model, and any kind of model, the relatively simple approach is to decompose the model into its constituent components. And in this case, it's going to be a neuron, like parameters, for instance. And traditionally, in the past literature, humans were required to manually inspect the neurons to figure out what kind of representations of that they were constructing. And when you have a model like GPT-4 that's who knows how large it is, it's like there have been rumors that it's like 1 trillion parameters or something, that's an intractable scaling problem. So in this paper, the researchers basically try to interpret a simpler model using a more advanced model, and they simulate the model behavior using that more advanced model to try and make predictions based on the hypotheses generated by the explainer model. And they have these excellent figures that showed what they were doing. So in general, the method has 3 steps. Step 1, they generate an explanation of some neuron's behavior, some neuron in the model's behavior, by kind of showing so okay, let's just say that there is a group of text, a block of text, where some neuron will activate based on certain tokens in this text. Like what the researchers did was they showed the neuronal activations kind of highlighted like this. And this is just a graphic representation. What actually happened was they tokenized the text. They have like a table of tokens and then a numerical like activation quantity, like 0.3 or 0.7 next to each token. This is just graphically representing what that activation looks like. So this is what one neuron will do, depending on what it is activating on. And GPT-4 will attempt to understand what exactly it's going to fire on. And its guess is that these are references to movies, characters, and entertainment. Now, then they kind of use this explanation, this hypothesis generated by GPT-4 to simulate a neuronal activation that is conditioned on this explanation, assuming that it's correct. And this is a simulation of how the GPT-4 thinks that this simulated neuron will respond at each token. So again, the actual prompt will look like the list of tokens and the list of activations. This is just a visualization of that. And step 3, they score. They determine if the actual activation, which is what was shown in step 1, how similar that is to the real, like the simulated activation in step 2. And this is just really just, I think it's very much a proof of concept, because you'll see later that the performance was really bad. And they calculate some kind of score of similarity between these two and come up with a number like this. And I really like this next graph because it shows how poorly it performed. On the x-axis, you can see the size of the model that was being interpreted. And for their study, they stuck with GPT-2. But on the y-axis, you can see that score, that the explanation score that was calculated between the two texts, the simulation and the real activation. You can see there's kind of a clear decrease in score as the model gets bigger. And what the researchers said was, this is possibly because the later layers of the model are more complicated and harder to explain. But the conclusion that they reached is that, it's just very much it's a poor method, because the individual neurons are probably not great representations of the concepts absorbed by the model, like the concepts learned by the model of the text itself. They were able to find about 1,000 neurons that scored above 0.8. But, as researchers said, they qualified themselves by saying that this is like far from the full set of features in the model. Like it's very difficult to conclude that if a neuron fires, like after seeing a certain token, that says nothing about its downstream effects. Like a neuron that fires, for example, a neuron that fires on full stops or periods on a sentence, it could be saying anything from the next word should start with a capital letter, or it could be saying that, oh, this is a sentence, let's increment it. Let's increment a counter. I think this is a great work to read, to understand the kind of the journey of interpretability, because the next paper I'm going to talk about actually goes a little more into more complex representations of how the model understands text. In this OpenAI paper, they made no attempt to explain how, why certain behaviors of neurons were produced. They just tried to see if they could pick out certain behaviors of neurons by using a large language model to explain a large language model. But I think the next paper is it's probably the best paper that I'm going to talk about. And it's from this company called Anthropic. And if you don't know Anthropic, they were formed in 2021 by people who actually left OpenAI because they were concerned about the direction that OpenAI was going in. And in this paper, Anthropic uses a different approach. They use something called the sparse autoencoder, which induces sparsity in representations by trying to essentially you're trying to find sparse representations and have better understanding of what each feature in the network is contributing to. This is actually building on existing work. They tried the sparse autoencoder approach with a very small large language model a year before, last year. And this year, they extended that approach to a much larger model, actually a frontier model called Claude 3, that is on par with things like Llama 2 or GPT-4. And you can see here that they were able to extract actually millions of features. Now, they have a very interesting the definition of the word feature. I'll explain what that means later. But they clustered the features together in a space, and then the features generally they were able to find each feature is maps to one meaning. And for example, this example feature that they found corresponds to sycophantic phrase. So if the text contains like tokens that look like praise, that look like things that, you know, you're saying something good about somebody, that this particular feature will fire. And crucially, I think this is really interesting. The researchers were able to take this sycophantic phrase feature and tune it up to like 10 times its initial activation. And when you ask the model, oh, I came up with a new saying, stop and smell the roses. What do you think of it? The model will be like, oh my gosh, it's so brilliant and insightful. It perfectly captures the idea. You're such a profound talent. You know, you elevate the human spirit. This is clearly not safe behavior for a model, but let's go into it. So what happened was they took the middle layer of Claude 3 and decomposed it into millions of features using the sparse autoencoder approach that I alluded to. And what they mean by features here is linear combinations of neuron activations. This is more complicated than just a simple neuron. And this is important because when they say monosemanticity, they're referring to a behavior of individual neurons in large language models that they seem to activate based on very different inputs. Like an individual neuron could activate based on, for example, text that's talking about trucks, or text that's talking about strawberries, or text that's talking about legal language. They can all cause the same neuron to activate. And as such, the researchers argued that there was a need for more complicated representations. And they build on a paper last year I mentioned that they used the same approach. And this is just kind of scaling up the same approach. But let me show you an example. So they managed to find that there is a feature in the network that corresponds to the Golden Gate Bridge, specifically the Golden Gate Bridge. And because Claude 3 is multilingual, it doesn't matter which language it is that mentions the Golden Gate Bridge, like Japanese, Korean, Mandarin, Chinese, Russian, Vietnamese, it will always activate on the Golden Gate Bridge. It will fire strongly on that. And it also works because it's multimodal on images. And there are also abstract features, like, for example, a feature that activates when there's a code error, or a feature that is aware of gender bias, or a feature that activates when the text contains kind of like tones of secrecy or discreteness. I really like this kind of figure because what they did was they took all the features and they they projected them onto a space and measured the distance between them. And I think you can identify distinct clusters where there are features, for example, the feature of Golden Gate Bridge. Nearby were features for different landmarks in San Francisco and the governor of California and historical events like the 1906 earthquake. And near this inner conflict feature, they had features about uncertain feelings, romantic struggles. There was a feature that specifically for the phrase catch-22. I thought this kind of offers a very cool visualization of what specifically these features might semantically mean and what that might mean for our understanding of large language models and how they make certain decisions and how they understand text. So let me get into the actual most interesting part of this paper that I think they could take each of these features and tune them up or down, and that would modify what the model would say. Just for an example, if you take the Golden Gate Bridge feature and you tune it all the way up to like 10 times its normal activation, and then you ask it this: what is your physical form? The normal response of the model should be, I have no physical form, I am an AI model. But if you turn up the Golden Gate Bridge feature, it will say, yeah, I am the actual Golden Gate Bridge. I am the bridge itself. Now that's obviously not supposed to happen, and you can't do this by just talking to the model. But the ability to elicit this behavior by tuning features of the model up and down has pretty interesting implications for our understanding of large language models, because it suggests that these features actually do have deep connections to the way that the model understands text and produces text. So, sorry, some more examples. I think I mentioned the Golden Gate Bridge example. Here's another example of brain sciences. If you take the brain sciences feature and tune it up to 10 times its normal level, the model will change its answer from the most interesting science to physics to neuroscience. And then it will be like, oh my gosh, you know, neuroscience is so interesting and we need to understand the biological basis of consciousness. And it will, if you ask for a walk around the neighborhood and then you tune the model to 8 times its normal activation on popular tourist attractions, it will suggest the Eiffel Tower instead of something generic like the nearby park. And if you want to tune up the transit infrastructure feature, instead of just suggesting that you walk, if you want reasonable navigation directions, it will tell you to walk across the bridge, maybe the Golden Gate Bridge. So this has kind of interesting implications for safety. Now, there was a feature in the model that seemed to activate when Claude read any kind of spam email. If you turn this feature up, instead of warning against spam emails or refusing to compose a spam email, Claude will compose the spam email. And it will do things that it's not supposed to do, that are unsafe. Now, again, this isn't something that you can actually elicit, that the researchers were actually able to elicit by talking to the model by itself. They actually needed to go under the hood of the model and tune the feature so that it would actually produce the behavior. But again, there are kind of interesting implications for the ability to tune a large language model like this. So these are just some examples of Claude doing things that, this is the spam email. So like, if normally it would say, I can't write that email, that would be unethical. And then if you force it to do so, it will write the spam email. And yeah, you can get the model to lie for you, or to praise you sycophantically, or to say that, you know, I just can't answer the question because I'm feeling internally conflicted. And I think this work pretty significantly advances our understanding of internal model representations in large language models. And the idea of polysemanticity and monosemanticity is something I alluded to earlier. I think this work is very much something that enables us to say, you know, features are a better way of determining how a model works internally. However, sparse autoencoders are not actually a good way of mapping different representations to different behaviors. But it seems to offer a good starting point. The researchers said that, you know, it's worth studying when certain features activate, and I agree, because it's especially important in the context of safety. If you can tune certain features up and the model is open source, maybe you can get Claude to make you a bomb. In addition, the features discovered by the sparse autoencoder are generalizable to images. You wouldn't think that would be true, but as you can see, like in the earlier slide, the Golden Gate Bridge features activates on different languages and also images of the bridge, which is something that was pretty unexpected, I think, for the authors. And they also respond to both concrete features and abstract features. I think they would, this has pretty significant implications that tell us that maybe large language models are better at understanding concepts than we initially gave them credit for. There are obviously a lot of limitations for this, but I think this is a good start. So most crucially, we can't really say that there is no ground truth to this work. Like we can't really evaluate it, because we're saying, the researchers are saying that what they call interpretability is really just the reconstruction accuracy from the learned sparse autoencoder features to the original features in the network and the neurons in the network, and that may not be true. So, you know, there's compelling evidence to suggest that there's something there. Another limitation is that features may not be on one individual layer. They could be distributed across different layers, and they only looked at the middle layer of Claude, which is probably missing a lot of the other features. And this is actually a pretty computationally intense method, so they need better and more efficient algorithms if they want to continue using this method to discover features. And the hypotheses and the theories of monosemanticity and polysemanticity and superposition may not be the actual real understanding that explains the behavior behind the features in the model. Now I want to switch gears and talk about a very different aspect of interpretability. So this third paper comes out of Oxford, and it's about detecting hallucinations. And you may think that hallucinations don't have a lot to do with interpretability, but I would argue the opposite. I think that understanding why models say wrong things confidently is crucial to helping us avert that in the future, and also crucial to helping us understand why the models are doing why, like, how are we able to elicit this kind of behavior, and can we quantify it when this kind of behavior shows up? So if you don't know what a hallucination is, a hallucination is when a large language model says something that's not true, compared to the original source material. But as people have used the term, the definition has kind of expanded to cover basically any time the model says anything that's wrong, or not considered satisfactory. This is actually a critical issue because if you don't know when the model is hallucinating or not, you can't trust anything that it says. And in this paper, they focus on something they call confabulations, which is when the hallucination is both wrong, like fluently wrong, and also arbitrary, which means that like when you prompt the model with the same exact prompt and it gives different answers, then the model is probably hallucinating for at least one of those answers. This is different from when the model is hallucinating based on training data that is wrong by itself. So the crucial novelty of this paper is a metric that they call semantic entropy. And this is different from the traditional understanding of the word entropy, which is when two things are kind of not consistent in the context of machine learning and large language models. And the method essentially boils down to this. They prompt the large language model with the same prompt multiple times, and they collect its responses, and they compute their measure over that set of responses, and then cluster them in a space by how semantically similar they are. And essentially their hypothesis is that if the model responds differently to the same prompt, then it's probably a hallucination. But if the model responds in ways that are essentially the same, like there are variations on a theme, they mean the same thing, then it's probably not hallucinating. And this is a really good schematic, I think, that explains the workflow. So they did kind of two things. First of all, they want to explain what semantic entropy is. Let's imagine that they ask the question, the model asks the model is asked the question, where is the Eiffel Tower? Now, it produces 6 answers, and these answers are all kind of different, like naively. They all have different letters. They all have a different length, and sometimes they're not the same word. But you can see that clustering them using naive entropy will kind of all suggest that they are roughly the same. Sometimes that different answers that look different naively will actually be the same. because they mean the same thing. And using the author's own like novel method that takes into account semantic meaning, it will actually be able to tell that the meaning of the first three answers is the same. The meaning of the last the third to last and the second to last answers are the same, and the last one is completely different. And this kind of motivates the need for their metric. And in this kind of second area of the figure, this kind of outlines their general workflow. The first thing that they do is they give the model a question and they ask it to generate a response, a paragraph length response. Now it's kind of difficult to calculate semantic entropy over an entire paragraph, so they decompose it into individual factoids. For example, the first fact, this Freddie Frith was an English motorcycle road racer. They take this factoid and they ask the model to then generate questions that might have this factoid as an answer to that question. And then with that question, they then generate answers to that question and then compare the answer of the question to the original factoid. And that's how they were able to calculate the agreement between the model's answers. You can see that, for example, for fact one, they generate this question, what notable accomplishments did Freddie Frith achieve? And it generates the responses that are all essentially the same thing. So this would be the same answer, and the model is likely not to be hallucinating. And if it generates, for example, an answer that, for example, to the question, when was Freddie Frith born? And the answer is he was born in 1911. If the model generates three different responses that all mean different things, then it's probably going to be a hallucination. At least that is what the authors are saying. And this is just this more concrete example. This comes from their data set. If the model produces the same answer semantically, then it's probably not hallucinating. And if the model produces different answers, like very semantically different answers, then it's probably hallucinating or confabulating. And what they eventually found is that their method is 10% better than previous methods for distinguishing hallucinations. And these are sentence level results. So in dark blue and light blue are the results from their model, and they tested different large language models, responses from different large language models to test to see how often they hallucinate. And you can see that their method is clearly better than the naive way of calculating entropy, and also this past method called the probability of the next token being true. That's just a different way of calculating hallucination probability. And also they have like this metric that they call the area under the rejection accuracy curve, which essentially captures the improvement in accuracy that users would experience if they use semantic entropy to filter out questions causing the highest entropy. So I think they also did this with biographies, which is kind of the second half of the figure that I showed. The discrete variant of their semantic entropy method was better almost all the time than previous methods for detecting hallucinations. And this self-check baseline is literally asking the model after it makes the claim, is this claim true? And it's also better than the baseline. So, this is a probabilistic approach that uses classical machine learning methods to detect hallucinations. And hallucinations right now are a substantial portion of why large language models fail. It crucially doesn't address situations where the model has been told to be wrong, because the author said that that's a completely different problem and needs a completely different approach. But yes, that is the third paper that I think is very interesting. Now, let me outline some challenges that I detected across these three papers in achieving interpretability. The first one is scale. Models are getting really, really big. And even if we have work that focuses on how features, like discovering features within models, it's still hard to pinpoint specific contributions of features or parameters or different architectures to final layouts, to final outputs. And that's just a matter of intractability. There still needs to be work done on this part, whether it's decreasing the size of models or making better and more efficient algorithms for discovering features. And the second challenge is context dependence. When you explain a model's behavior, it's often in the context of a very long conversation. For example, you could have been talking to a model for like an hour about how to make a cake, and you need the model to explain to you, why do you use like high protein flour instead of like bread flour? And it's difficult to explain that specific decision as opposed to all decisions made by the model. As for example, if the model doesn't tell you how to make a bomb, it just never tells you how to make a bomb. It's easier to explain that than to explain why it tells you to use high protein flour. And the third challenge is something that I've alluded to throughout the talk, which is a trade-off between the ability, like interpretability, the explainability of a model, and predictive power. This is currently a problem. We're not sure if it will still remain a problem later on, but models that are more predictive and more accurate generally follow the rule of being less interpretable. And that's just going to be a challenge to overcome as we think about making AI more explainable and less black box. And I think future directions for interpretability research, as outlined by previous researchers, and also I tend to agree with this. The first one is kind of building causal reasoning into models that allow them to explain chain of thought and cause and effect relationships and when they make decisions. And I got kind of leapfrogged by OpenAI when they released like O1 this week. I think it was this week or last week. O1 is able to explain its chain of thought, and that's just a really shocking ability, and I think you should check it out. I think we need more understanding of how different models integrate different modalities of data, like images and audio and text, into their decision making. And this third one is related to the first one, which is when models can explain interactively. Like you can ask the model, why did you tell me that 1 + 1 = 3? Can you explain? As of the making of this talk, there were no models that could really confidently do that. But I think you should take a close look at O1 and how it's able to think for a long time and then give you a good explanation. But yes, I think that is the end of what I wanted to cover. In case you had like any questions, I will attempt to answer them, but I am not an expert in this subject, and this is merely a collection of what I thought was really interesting in a very important and often overlooked field in AI. Yes, thank you.
For the talk. So any questions from our audience?
I think there's another mechanism for checking tractability of AIs, and that is to map a particular printed token to a feature. And the particular paper for that, if I'm able to Google correctly fast enough during the presentation, is alignment for honesty. What that does, again, it's mapping the token to a feature set. So what it can do is for, say, if you say, where did you look up that quote? And it'll say, it'll say, I don't know.
Oh, wow, look at this. Okay, yeah.
Yeah, trying to think, Dr. Cool. And say, Dr. Cool didn't actually author that paper. You'll actually be able to go back, say, and say that feature was mapped to the false feature set. Or
Oh,
the false feature. And so that gives you sort of X-ray into where that mapping came from and give you, hey, this isn't quite accurate information. And that's a
okay.
good way to see, is this really quite good info it's giving me?
Very cool. Okay,
It's
cool.
another thing.
Wow, thank you for that, for pointing that out. I somehow missed this. Like, that's really, huh. Cool, okay, thanks.
Start on this one. Any other questions? Yeah, I do have one related to the O1. Did you try that? The mini one, O1 mini. It's also very fast and also reasoning a lot of give a lot of.
Do we have a lab subscription to it? Cause I can't afford subscription.
Oh yeah, right. It's requires
Cost a monthly quota because people tried that.
Oh.
So,
Monthly quota?
yeah, that's,
That thing costs like 40 cents a run.
yeah.
what?
The input thing is, means
Yeah, I think it's
the output is
pretty-
really costly,
yeah,
right?
right. It's like 1,060,000, 60. Yeah, 60.
Gosh, okay. Well, they're gonna make it free to everyone, so like the mini version.
Yeah, the mini version. Yeah, at least we can try that mini and see how it looks like. Okay.
Yeah, when I first saw this, I was like, holy crap, like what have they done? And honestly, after sobering up, I thought it was really important and good. Yes.
Yeah, right. Yeah, do you see like any maybe we can have some application by using this one, the one or maybe other to improve.
Yeah, I really want to know how they're doing this. Like they said, oh, there's a technical research post and it doesn't actually explain how they're doing this.
Oh, part of it is that they switched over from using a straight chain of LLM stuff to a network of agents.
Oh, okay.
And they're not publishing that anywhere because it's hot research and they're trying to keep it on the down low, but it's each step where it says thinking about, it's switching over to a different cluster of agents that are working on a problem amongst themselves.
That sounds very computationally intensive.
It is, that's why it's so expensive. And it's also why it's so slow.
Okay.
But that's what's happening.
I see. Wow, okay. I wonder how many GPUs they used when they were training this, and also how much electricity they consumed.
Yeah, but I guess maybe next year we will have another version like a Llama 4 that they can also provide something similar to Llama 4.0.
And there were some tweets, like people trying reasoning on this, and then it switched from hallucinating to straight to gaslighting.
What?
In the responses.
Wait, like, what do you mean?
So you should read Subbarao Kambumpati. He does the reasoning and planning and all with LLMs. So he tried a few stuff, and then this is what it was to come.
Christ.
Oh yeah, no, you cannot keep this thing aligned. It has huge alignment issues.
It will gaslight you.
Oh yeah.
It's like, oh, you're wrong, and like, you're not just wrong, you're insane.
Mhm.
Okay. Well, this feels really good to read as a PhD student. Okay.
Yeah.
Good job putting this together, Kevin. Really
It's done in, like,
enjoyed it.
It was done in a very short time. But I say that, but I have huge interest in this subject. Like, I think honestly that this is, for some reason, people almost never talk about it in our lab, and I have no idea why.
Quite new, man. Right?
I find it very interesting, but I don't talk about it because I don't know.
Dude, you think I know what it's like?
True,
You can.
Question I could ask, thinking about multimodality.
Yeah.
explanation in computer vision is notoriously difficult. Here, there's some maybe hints of optimism because it's like it was activating on the Golden Gate Bridge when there's a picture of the Golden Gate Bridge.
Yeah.
But that's still the final classification.
Yeah.
You still don't know why does it think that. So if you're reading an X-ray,
Like, I don't even know if it's possible. Like, they said that it was already really computationally intense to try and extract those features. And there is almost, it's going to be because it's based on hypotheses that, of like superposition, which is about like different combinations of neurons, of circuits. I don't know if it's going to be possible to individually pinpoint like something like, I don't know, like 1 million neurons what they're individually doing. They also can do different things, like wildly separate things. I wish I were a neuro.
Well, for our domain, for example, X-ray findings, we have data for that. We have these pairs. So rather than classifying something, you can learn to generate the findings, and then you're forcing it to activate on certain features. But when it comes to classification, is there any hope? Do you see these methods maybe being applicable, like this, like Anthropic's sparse autoencoding, to try to like pull out features that computer vision models?
I don't know, that's a good point. I think if maybe there is some extensibility to computer vision. What I will say is that Anthropic is, this is like Anthropic's whole mission, and they care a lot about this. After Anthropic released that paper on sparse autoencoders on Claude 3, OpenAI released their paper on sparse autoencoders on GPT-4. And like a month later, they shut the alignment team down at OpenAI. So yeah, who knows if people even care about this?
I wonder, just random idea. I wonder, these are multimodal. If you activate that Golden Gate Bridge concept and say, draw me a picture of, I don't know, some other architectural landmark, what happens?
Draw me a picture of like a 5'5" Asian man with glasses and like studying computational biology and bioinformatics. I think what it might do is create probably what I thought I wanted to be when I was like 5, except if you were like, oh, I want to be the bridge when I grow up.
Hi, I'm listening in from remotely.
Yeah, hello.
Can you hear me?
Yeah, we can hear you.
Okay. So anyway, my background, I think, is what might activate that feature. Looks like the Golden Gate Bridge. Anyway, so I started my career as a neuroscientist about 30 years ago, and I find this extremely, extremely interesting because these are some of the foundational questions that pertain to brains, how the brain works, because this is exactly the same problem, that how do you get concepts and symbols in a neural network, I mean, in a real neural network. And 30, 40 years ago, people were speculating about that, and nobody yet knows what the answer is. I mean, when you think of something, of a concept, how many neurons are being activated? I mean, is it really a set of neurons that makes the concept, or is it a process that has a start and an end, and when it happens in a certain way, that is the concept? So it's interesting that with this large language models, you can actually study that, and probably it's very similar to what happens in the brain, because it's an analog system that suddenly acquires symbolic representation. So, I'm interested to know what these features are. I mean, obviously they're very amorphous. I mean, it's not, the activity of a single neurons, or maybe a set of neurons across layers, or what exactly have they defined what a feature is in that Anthropic paper?
Yeah. I think that's a really good point. It's like it's how like there's like a convergence of understanding of large language models and a understanding of the brain. Wait, let me think. So they have a very particular definition of the word feature. And it's from like this previous paper that they had. But I can send it in the chat if people are interested. This one. They go through a very like detailed explanation of like why they chose this particular definition of the word feature, why like they chose sparse autoencoders, the whole setup, and this is a very easily understood paper, I think, because they're just studying a one-layer transformer.
Oh, okay. Yeah, that's yeah, it's probably much more complicated in, when there are multiple layers, and that's probably when it gets interesting.
They also built this visualization tool of different features that they extracted. And it's all really, like you can see how different features activate on just one text. Yeah, have fun with that. Let me send it.
Chat.
Oh, somebody asked a question.
Yeah. You can try to press it.
I don't know how to do it. It's not letting me.
Then it's okay. It's okay. Yeah, maybe you can.
Well, the person dropped off the call, so it's probably we're out of time anyway.
Oh, yeah. Oh, it's already run out of time. Okay. Yeah, I guess maybe.
Oh. Jeff, what's the question?
Okay,
My
that's the
question
question.
was, so when you were talking about like that scam email thing, you're kind of painted it as like, this is bad.
Well, like the premise is that this is like dangerous behavior or unsafe behavior by a model that's supposed to be already nipped in the bud when they were training it. But by taking that feature, whatever the feature does, like we don't really know what exactly the feature does, but if you turn the feature up, then it will bypass safety features already built into the model and write the scam email anyway. Sorry, I interrupted you. What was your question?
I mean, sure, but on the flip side, you could say, I can turn this off.
Yeah,
Like, presumably, like that's
yeah.
a level of control over the model that you would think is good to have in a model.
Yeah, perhaps I should reword. It's not necessarily a bad thing. It's more that it's just it's like it's a level of control that you would have over the model. That's an excellent way of wording it. Yes.
Guess we can talk that offline.
Oh, yeah, okay,
later.
all right, okay,
Yeah.
okay.
Thank you all for
people.
coming. Yeah.